And hi, everyone. My name is Ranjan. I'm a sales engineer at JuliaHub. And today we're going to talk about FMUs. Really, how exactly do you sort of ingest FMUs into JuliaSim? How do you run FMUs in JuliaSim? How do you deploy FMUs in JuliaSim? And to sort of spice things up a bit, we'll try to generate an FMU of a surrogate model that we generate or train in JuliaSim. So to give you guys the agenda for today. So first we'll start off, just a level set with everyone, just give you a little bit of background on what is Julia, who we are, what is JuliaHub, who we are as a company, this notion of SciML and really what, and how it relates to JuliaSim, which is sort of our modeling and simulation product. And then we'll go and start discussing FMUs, introduce FMUs if you guys haven't heard of them before. Sort of propose a couple of ways you could use the FMI interface in JuliaSim to sort of speed up existing models and so on and so forth. And we'll go through a little demo of building sort of this vapor compression cycle model, an HVAC system in JuliaSim, and then train a surrogate model of that HVAC system before we deploy that surrogate model as an FMU, and we'll sort of see a little bit at the end where we run it in an external simulator as well. So what exactly is Julia? Julia sort of, this is a language that's a sort of a high-level scripting-like language, much like Python or R, but that happens to be much faster. If you look at when people talk about programming languages, one of their favorite sort of charts is to look at a performance productivity metric. And if you look at this particular chart here, you'll see Julia is on the bottom left, which means more expressive and as fast. This chart does not come from us. This comes from the folks at Chapel, which so these are not our tests as well. However, you can see that Julia sort of with the can give you the performance of languages like C, C++ while writing scripting code, much like Python or R, and that really is the promise of Julia. And yeah, I mean, so if you have sort of scripting language that can write code much like C, C++, it's sort of there's a lot of folks out there writing simulation codes in Julia, and yeah, and so what we do as a company is we build products for Julia users, and to give you a sense of that, we as a company provide a platform, a cloud-based platform called JuliaHub, which is sort of a platform as a service. It has which has a bunch of different enterprise-ready features, such as security with SOC 2 compliance and so on. But really, we provide all of our products, our sort of domain-specific products through the platform as well. So JuliaSim, our sort of physics-based modeling and simulation product, is provided through JuliaHub, and of course, JuliaHub acts as a complete and total compute engine as well. So, for example, most of modeling and simulation, and a lot of workflows in modeling and simulation involves grabbing large amounts of compute, whenever we want it. So, for example, you've built this really complex model and you want to simulate it, and you're on your desktop, which perhaps is not as powerful. Can I grab a really powerful machine and sort of set off a job to simulate and then look at the results later, right? And that's sort of the value proposition as we provide our products through our cloud platform. Right. So now JuliaSim itself is one of these products that we provide through the platform. It is the subject of today's webinar. And the way we like to describe JuliaSim is it's scientific machine learning, for our enterprise customers. And what does that really mean? So to tell you what that means, it's important to introduce the notion of scientific machine learning. And but really the way we like to think about scientific machine learning is sort of AI, so to speak, with the robustness of classical modeling. So really, we're not throwing away any of the tried and tested modeling techniques from the past 50 years. In fact, we embrace them. But how really can you sort of employ the latest data-driven methods that exist out there in the machine learning universe and sort of compose them with these classical modeling tools, right? And so our attempt at this, or let's say or SciML's attempt at this is the notion of making all of our simulators differentiable. So can you easily get the gradients, the sensitivities out of your models natively? And that's sort of really something you can do with in scientific machine learning. Can you build reduced order models and representation and surrogate models and so on and so forth of your physics-based models? Absolutely. That's another sort of core feature that now, and then can you use because your models are differentiable, can you sort of calibrate them to data easily? Can you use can you do a sophisticated maybe systems identification type of approach where you discover new physics, discover new equations that could be augmented with your model, right? And all of these all of these ideas, so to speak, this confluence of ideas is what we generally tend to refer to as SciML. So the but to bring all these ideas to our enterprise customers, we've built JuliaSim. So what JuliaSim is it sort of builds upon an open source foundation as is most of our products. So you build upon the Julia ecosystem, the SciML ecosystem, and then we have an open source modeling language that's out there. You can download and use it today, called Modeling Toolkit. It's sort of a very sort of equation-based acausal modeling framework, where you can sort of easily build up models and compose them with each other to build really sophisticated models. To get our customers started quickly with Modeling Toolkit, we provide a rich suite of standard library models. In particular, the HVAC library model, which we'll demo today, as well as our batteries models. And of course, we have a multi-body library as well, in addition to our standard library. And then on top of the models that we provide, we give you a suite of methods that sort of incorporate all of the ideas in SciML, right? Like and sort of build on top of the SciML open source ecosystem. So can you discover physics, additional physics, with the data that you're getting from the field? So let's say you have a physics-based model and it doesn't quite match the data in the field. You could sort of try and calibrate it. If that doesn't work, can you discover other sort of higher order terms or friction-based terms or things like that you're missing? And you could use model discovery to sort of infer those. Can you build robust control systems? Using the models that you've designed in JuliaSim. That's another sort of suite. That's another sort of product library that we have. And then can you build surrogate models to accelerate every part of your design process? And so we provide sort of a nice duopoly of models and methods, for our users. So just to summarize again, how can you do all of these? Can you design, discover, calibrate, control, and build surrogate models in JuliaSim? So what are we? So on to today's webinar. So what exactly are we going to show you today? We're going to talk about how one might sort of import FMUs and export FMUs in JuliaSim. So just to level set again, if the FMI standard is sort of a very widely used standard for exchanging dynamic models. It is supported by about 180 tools out there. So most of your favorite vendors probably support it. There's a really nice list in FMI.standard.org/tools that tell you exactly what is supported. Highly encourage you guys to check it out. But yeah, so it's an industry standard that's adopted out there. So with JuliaSim, we sort of leverage the standard for like two broad workflows that I will say that we can think of with the FMI standard. So the first one is what I'm going to show you a bit of today. And I'll talk to you about the second one. But the first one really is, can you build a model with the standard library components from scratch in modeling toolkit in JuliaSim, right? And let's say you've built that model, and then you have a legacy model, and then that you might find that the JuliaSim model is much faster, given how fast Julia can be. So can you then take that model, make it realistic by calibrating it to field data that you receive, and then can you well, excuse me, this is a typo here. So can you then sort of train a surrogate model with this with this finalized sort of calibrated model, right? And then once you have the surrogate model, this really fast surrogate model, which is even faster than the Julia model, can you export the surrogate model as an FMU and then import this as a block into sort of your external tool, and which can be much faster. So that's one sort of workflow that we've seen, that we've spoken a lot to a lot of our customers about. So that's roughly what I'm going to demonstrate today. And the second one, which is again also fairly interesting for a lot of folks, is like, let's say you have a lot of legacy models, right? And most folks have a ton of code, in some tools and you can't possibly rewrite them or even start from scratch. So can you export those tools using the FMI standard, right? And why might you export them? I mean, perhaps they have a ton of performance issues. Perhaps they're very large and unwieldy, difficult to understand, and very slow, very expensive to simulate. So can you export FMUs of those, import that into our tool, and you can just directly use our surrogate modeling techniques, the data-driven stuff, of course, to just build a surrogate model of your FMU simulation, export the surrogate model as an FMU, and then import that new surrogatized FMU into an external tool for that 100x speed up. So that's sort of really the two ways. So the first way starts of design within JuliaSim itself, which I will show you, and the second one is sort of can you bring your models into the tool so as to be able to take advantage of our methods, right? So that's sort of this two-pronged approach that we sort of foresee with the FMI standard. By the way, if you guys have any questions on anything that's come up so far, just feel free to put them in the Q&A bar there, and I will get to them. Right. So how exactly one might start building these models in JuliaSim? So we have sort of a fairly rich model library. Of standard components. As I said earlier, we have a standard library. We have specialized HVAC components, battery components, multi-body components, and we have a number of libraries in the works as well, which are listed over here. But here's the key, right? I mean, we have a roadmap for how we're building out these libraries. But if you'd like to sort of comment or sort of have any input into that roadmap, we are more than happy to listen. And I'll leave a few sort of call to actions in towards the end there, so for you to get in touch with us. So I see that there is a question. What about sequencing FMU models that of different origin? Can that be done as well? So I mean, yeah, absolutely. So we can definitely we can definitely import FMU models from a number of different simulators, and we can also sort of sequence the simulations or co-simulate all these FMUs together. That, yeah, we can absolutely do that. I mean, that's no There's no question that I think. I mean, it's really a question of how you want to do the orchestration, like depending on the various simulations. But there's plenty of flexibility within. You know what? The nice thing about JuliaSim is that it's built upon Julia, like a full programming language, and really that comes with a lot of flexibility, which you can do. And you can of course compose those co-simulated models with native JuliaSim models as well. So so yeah, yeah, so yeah, we have a bunch of standard library components. So if you'd like to sort of add to our roadmap there, please feel free to, just sort of yeah, just reach out to us and we can have a conversation about that. So our modeling toolkit standard library, which is also open source, is consists of a number of standard components, mechanical components, thermal components. But that's just sort of that'll really sort of help you just get these get started very quickly. But the other sort of very specialized components that we're building out are our batteries models and our HVAC models. So to give you sort of a quick sense of our battery models, we're building full P2D, full pseudo 2D, Doyle Fuller-Newman, DFN models, SPM models, SPME models, just sort of physics-based models, and we can scale easily to packs and modules, and and very quickly, and we are much faster than a lot of tools out there. So so again, that's the thing with any of the Julia tools. You definitely get speed. So the nice thing about these sort of battery models is that you can now import them into JuliaSim and compose them in sort of a multi-physics simulation, and with regard to you can compose, you can build controls, battery management systems, and compose them with motors, inverters. That's so all of this stuff is all is possible with the JuliaSim ecosystem, and this is just a sort of a standard library within the ecosystem. So so you could have a full battery pack and sort of design a really high fidelity battery chiller, right, that composes a cooling system with the battery pack, as an example. The other standard library that we have is the HVAC library, which was developed in collaboration with Mitsubishi Electric. So we licensed the properties from them, and we license some property models and data from them, but we build out the entire sort of stack, and just in general, just even simple models like this vapor compression system are usually much faster when built out in JuliaSim and Julia than many of, let's say, some Modelica vendors out there. So we've seen this in the past as well. And really, once you have these models, one of the things that you might want to do with them to accelerate every part of the design process is build surrogate models. So can you take an existing physical model, identify key outputs of interest and sort of key inputs, right? And just sort of feed that into our software system and then have it all churn, just sort of churn and train and then give you a report and a surrogate model at the end, which you can then deploy as an FMU, do other interesting things. Now, we get a lot of questions around how one might train surrogate models, and because we're cloud native, we can sort of amortize the costs of these simulations required to sort of train these surrogate models. So just another question. I'm saying, can the FMU accept real-time data input from a lab experiment? Yeah, the answer is yes. That's sort of that's on our that's on our sort of product map to test out. We can already probably do it, but this is something we're actively testing out. So can you take in real-time streaming data, for example, and then and forget even an FMU, right? Can you sort of deploy it? Can you sort of ingest it into a live physics-based model deployed on the cloud and have that model update in real time, right? And that's a suite of capability that we're developing, and that's sort of the direction we're heading in. if that helps. But yeah, I mean, in general, yes. I mean, there's ways to work with streaming data as well, even today. So right. So just as an example, as I said, this is the surrogates example we're going to look at. This is from a slightly different model than the one I'm going to show you today, because just because we're doing a live demo, the model I'm showing you today is a bit simplified, but really you can get a couple of orders magnitude speed up out of the surrogate model, which honestly should not be very surprising given that surrogate models. So the way the surrogate models work is that they sort of build a new dynamical system from scratch, and you can construct that dynamical system how you want with the simulation data that you're taking in. So it's not that surprising that you get these kinds of speed ups with these surrogate modeling techniques. The key challenge, of course, is the accuracy, which you have to keep testing out, and we'll show you how to do that as well. And as I said earlier, because we're cloud native, we can do all of this stuff. We can amortize these sorts of simulations on the cloud as well. All right. Before I show you that, maybe I could go straight to the demo. So maybe can you guys see this demo? Let me just double check. Yeah, I think you can. So all right, so this is JuliaHub. This is sort of our platform, at least the internal version of it. But maybe before I go there, yeah, so I have a question on what are the parameters that were trained in this example. So maybe I'll just go to the demo and just sort of show you just an example. So now, so this is JuliaHub. You get a bunch of apps, with JuliaHub. JuliaSim lives here. All of our other products live here, and so one of the ways you can interact with JuliaSim is through this app, which gives you an integrated development environment, an IDE, which is VS Code based. So as I sort of build up to the as I sort of tell you as maybe the right place to start is to show you how to ingest an FMU. So we use for ingestion, we use a package called FMI.jl, which is also open source. So really the stuff that's open source is building some standard library components, the modeling language itself, and things like importing FMI, right? The stuff that's closed source is all of the methods, the surrogate modeling, the HVAC components, the battery components, multi-body components, all of that stuff is sort of closed source. Anyway, so this is how you let's say load an FMU within JuliaSim, and then it's sort of really simple. It's just a load command. Here the FMI within the XML will have these these inputs and outputs specified. We grab those and then we just call a function called FMI simulate. And yeah, and if we just hit the plotting function, we get the outputs here from this sort of FMU. All right. So just to give you a sense of the model the model that we're going to build a surrogate model of, right? So I'm just going to quickly show you how we're going to build up this vapor compression cycle model. So the other sort of thing I could mention is that some of the stuff is sort of captured in some papers that we've published, so I can I can sort of show you where you can get the exact parameters and data for which we're showing you all these results. This one I'm sort of doing live, but the other stuff that are in the slides, I can we can send across some references as well. Anyway, so our library is just called HVAC, and what we're going to do is first define what kind of refrigerant we want in the HVAC system. define all of our parameters, and the components that we're going to define, and all of this is in our documentation as well. HVAC here, vapor compression cycle. So you'll see. So we're just going to define a simple condenser, compressor, evaporator, and LEV. So you can sort of if you're if you're very particular about how you want to set up your components, you can sort of set up we have a model here called a typical compressor, which you can just use, a typical expansion valve, which you can use. You can define some parameters here that dictate the finite volume discretization of the heat exchanger, and then and then start defining some sinks, an evaporator, some boundary conditions, and just sort of just like how just connect these various components with each other, in this fashion. And again, like if you guys want more details on the specific parameters we use in the system, I would go through this documentation, which will get into really how you should set up these systems. So these are all the parameters we fit in the compressor. These are all the parameters we fit in the valve, and so on. And you might see that there are a lot of things that we specified here, but just as in the interest of transparency, to make sure that you know exactly what you're building when you're making your models. So so once you've defined all of your equations, once you've defined the circuit, right? Like you've declared your components, you've defined your equations that connect all your components. So typically in Modeling Toolkit, you set up this thing called an ODE system, which takes in all of the equations and your independent variable, which is time. Your system model is a composition of all your components, and then really you do this. You then start the compilation process for the model, which is sort of called structural simplify. So once this is done, this should start. You should simplify the models, and maybe to get a sense of the simplification, this compilation took about 2 seconds, but the simplified model has 73 equations, whereas the original model had like about 1,000 equations. So after we write a bit of code to set up our defaults, we can then hit solve and then stare at a plot, and sort of validate our system, and then sort of see how and see how it works. Yeah, and really at this stage, if you're looking at a plot of your system and you think that it doesn't quite look right, and maybe you have some field data that you want to calibrate it to, then then in JuliaSim at this point you would import the data, and then you would run some calibration. I'll refer the audience to another webinar that we've done on exactly how you can do all of this calibration and sort of set up all of your model and validate your model, which we covered in a previous webinar. We'll send that out as well. So now you can look at a few plots and sort of, let's say, be roughly satisfied that this model is validated. Now, finally, now that you're satisfied with this, and let's say you want to perform a design optimization loop, right? And let's say this example, which would simulate it in a sub-millisecond, but let's say this example was really expensive, right? And you want to use this in some sort of design loop. So one of the things you can do is generate a surrogate model. So how might one do that? So in JuliaSim, our surrogate modeling architecture is what we call the digital echo. It's just a name for a surrogate model. You can so the digital echo code, just operate. The way you set it up is just you go through a few stages. So the first stage is, of course, specifying the model. And instead of writing all of that code, which I showed you in the previous file, we have sort of a simple way, like a 10-line way of setting up the same vapor compression cycle. But let's say once we set up this vapor compression cycle, what we're going to do is sort of decide what our inputs and outputs are going to be. So in this particular case, we've looked at excuse me. Yeah, so we have picked, let's say, 6 parameters that we would like as inputs to the system. So these are the sort of 6 parameters as you can see, there's some mass flow rates in here, and some pressures. But once you pick these, parameters, and if you guys want to see exactly what these parameters are, you should probably be able to see. You should probably be able to see it here, right? Now, let's say once you've picked these inputs, what you have to do is tell the surrogate models how many data points you want or how many simulations you want to train the surrogate model with, right? And in this particular case, we're choosing about 100 simulations. And so, we're perturbing by, plus or minus 10%. Just let's say we want a surrogate model that is just accurate within 10% of this model's sort of nominal operating range, or let's say nominal operating parameters, right? So it can generalize across, plus or minus 10% of these various parameters. So then we define, you define this notion of a parameter space, and then you feed that in. We feed that in, and then you simulate it. So now I've sort of, commented this out because it takes a while to simulate. However, once you hit the simulate button, you get something called an experiment data object, which is why it's called ED. So to show you what this experiment data object looks like, let's go down here. So this ED is essentially an encapsulation of all of your full dynamical system. So how many how did it do the sampling across the input space? Or let's say it did the sampling across the input space. What are the full statistics on the system? How many initial conditions did you use? How many parameters did you use? How many initial conditions? How many parameters? What are the statistics among some of the outputs? In this case, the states are the outputs. So it gives you all of this information in this nice little, nice little table here. But really, it's essentially like a full dictionary of information, right? And its display object is just giving you this aggregate statistics. So now this sort of, in our view, encapsulates a full training data object. Which is why we call it the experiment data. And of course, this experiment data needn't to be simulation data, right? This could be field data that you take and then you try and run a surrogate model to fit that field data. So the notion of separating simulation and training makes a lot of sense to us. So once you've generated this experiment data object, you can now hit train on a surrogate model. And what that means in this case is to just run this command called digital echo on it. And so what I did is I've just trained this for about 100 epochs, looked at the training, and so on and so forth. And of course, because we're doing this live, I will just load the surrogate model today. But if you sort of look at the surrogate model, you get a bunch of hyperparameters over here. So yeah, this surrogate model is sort of a reservoir computing model. So you'll see some hyperparameters there, like R size and so on. And now it'll tell you what solvers, so this is a full dynamical system, and which has a solver baked in, which is going to time integrate it. So see another question. Can the field data be sets of data captured at different sample rates? Yeah, absolutely, we can. So we have, so if you look at the, so if you look at this ED over here, it's essentially a dictionary. So it has this thing called TSS. Oops, not that. Sec. Let's see. So anyway, so I think I need to grab this pre-processing. Anyway, so let's see if this works. Actually, you can convert this thing into a dict. Pre-processing to ED to, what is it, JSS base. So you should be able to convert this into a dictionary. So what you're going to see, and I actually do have some code here to show you that. Yeah, ed.specs.tss. Oops, sorry. Allow. Yeah, so you'll see here that there's a bunch of information in here where you can actually get ed.results. That's what I was looking for. So ed.results.tss. So you see here, so this results.tss object actually contains a bunch of different time spans, and you can use different sort of, so this can be a number of different, so the, or vals, I guess. So here you see that in this particular case, that's just, we have a time span of about 300 seconds, and then it's captured a bunch of time steps over here, right? This can be completely arbitrary. So the second simulation could be at a different frequency. Third frequent simulation could be at a different frequency. It's all different. The system is smart enough to understand all of that. So yes, absolutely, you could have time at different frequencies. I hope that helps. Yeah. So, all right. So let's say you've loaded the surrogate model, right? So now, well, as you would naturally do, you would define a validation space and then pull in some validation data. And to get a quick sense of whether a surrogate model is actually trained, you should start getting some plots right away. So you get so we can see that our surrogate model has trained quite a bit, but there's a tiny bit of error, as you can see over here maybe, but largely speaking, it has trained quite well. Even when we are looking at validation data. So of course you can take the system, just sort of do this quick sanity check, or you can take the system and have it generate a full report for you. But really once you've done all of this validation, you can then run a one-click function called deploy FMU, which takes in your surrogate model, and your ED because of all the statistics that it has, and then it'll just give you the FMU. So in preparation for this, I have generated this FMU in advance. It's called digitalecho.fmu. So what I can show you very quickly now, if I can, yeah, much better. So what I can show you very quickly now is now I'm just going to try and see if I can run this FMU in another simulator. So I'm just going to open Python. There's a sort of very very nice simulator called FMPy. So what I will do is import FMPy, and I'll just run simulate. And when this thing loads, when we hit simulate, it's going to have you're going to get a lot of these logs here, sort of intentionally in this particular case to show you what's going on. And these logs, you can see that's simulating the system, fairly quickly. But you see, but if I can scroll back up to these logs, sometimes when you have a lot of states, there's a lot of output. Anyway, the logs should show you like an entire sort of Julia runtime initializing and just sort of, it's so the Julia runtime is completely sort of compiled down, and you get a nice executable. And so this call opens the Julia runtime, runs the simulation in the model, and then gets the results and closes. So let me get back. Let me show you the code there. So this is another question. So does the FMU have to be model exchange co-simulation or either? So the FMU can be anything. So this particular FMU that I've gotten for you is both, has both model and co-simulation, model exchange and co-simulation in it. The advantage with deploying JuliaSim models as co-simulation is that you embed the solvers in there, and our solvers are quite fast, and so you can take advantage of these solvers. Yeah, so that's sort of the trade-off you're making there. In this particular case, we have, it's both model exchange and co-simulation, although I'll have to double check whether I just exported this one as co-simulation. But yeah, but what I ran just now was just co-simulation, just as an example, but we can do both. Right. So that is so that's largely what I have for you today in terms of like demos and material. So are there any other questions that we can talk about? I mean, I think really what I wanted to sort of plant in your heads is there's all of this information and all of the stuff is in our documentation. So to get to our documentation, just go to help.juliahub.com. It'll take you to this landing page. There's a JuliaSim tab in there, excuse me. And you can go look at our batteries models, HVAC models, and examples. The digital echo is in here. There's a lot more in the digital echo than I showed you today in terms of every part of the surrogate modeling process is compute intensive. So can you spawn these off as batch jobs? And really, Julia, the digital echo has all of the stuff built in, right? So can you set up a data generation script called, with this macro data gen, and just, and you put your unwieldy model in there, and just hit and just say, and then you should be able to just call data generation, which should be somewhere. Yeah, so you can define a particular computer for on which you want to run this, and and call a batch image and just run a data generation job, and then it should just spawn off. It'll run all the simulation and then save it as a JuliaHub data set, which is sort of the primary way we ingest data into JuliaHub. So yeah, I mean, there's a lot here, and then another sort of interesting example I'll have, maybe I'll just quickly go through for you guys is, can you import an external FMU into JuliaSim, run the surrogate modeling, and then export an FMU again? And so this particular tutorial shows you how to do exactly that. So yeah, I mean, there are a lot of examples here. So I encourage you guys to go to our documentation. And of course, we are sort of very eager to talk to y'all. So if you have any questions, just email us at sales@juliahub.com, and I can get on a call with you guys and just sort of walk you through everything and tell you exactly what you may or may not need. So yeah, I mean, yeah, and just as a final note, we'll be at this conference next month called the International Battery Conference, so a battery seminar, in fact, so which is on March 12th to 15th. So if any of you guys are in town for that one, do give us do come and say hi. All right.
Thanks a lot, Ranjan. In case any of you have questions, do type it in and we'll take it in the order it comes in. So we'll be around for some more, maybe a couple of more minutes, and see if there are any questions come up.
Yep. I just got a question that said thanks. So You're very welcome.
And the video of this webinar would be emailed to you as well, so that you can refer to it in case you want some information later in the future.
Yeah. So there's another question is, if you don't use the solver with Julia, will the results be accurate? I mean, generally speaking, yes, it should be fine, like in terms of accuracy, if that's what you care about. Of course, there'll be some differences, right? Because different solvers work differently. So if you're sort of importing, importing in an FMU into a Modelica environment, and you find that it uses DASL, and you might have used a different solver to sort of set up your system earlier and validate it. I mean, of course, there are going to be minor differences, but largely speaking, not really. It's not going to be wildly different. Yeah, I mean, I think if there are no further questions, Sanjeev, I think we can call it.
Yes, we can call it a day. And yep, thank you, everyone. We regularly organize webinars on various topics. You can look for our future webinars on our website in the events section, and register for any of them if you can.
Yeah, sorry, Sanjeev, there's one last question. Can multiple system model FMUs be ingested to have the same ontology? I'll have to, I guess I guess the answer is at the outset, yes. I mean, I think if you have a very specific sort of use case, do get in touch with us, and let's just you get all of your FMU models, and maybe we can set up a demonstration for you. I'd say that's maybe the easiest way to. We are quite accessible, so we can maybe just set that up for you. Yeah, now I'm truly done, just Sanjeev.
Well, I think no more questions coming in,
Yeah.
so we can call it a day. Right.
Yeah. All right. Thanks,
Okay.
everyone.
Thank you, everyone.
Join us. See you in the next one.
Right. Take care, everyone. See you. Bye.